we want to know what happens to it as it gets really close to 2. So that's why we have a little chart. And in the chart, we have our x values pretty close to 2. So 2 is in the middle. I have numbers that are on the left side of 2, so 1.9, 1.99, 1.999. And I have numbers that are really close on the right side of 2, so just beyond 2. 2.00, 2.01, 2.1. So in your calculator, we're going to see if we can use the calculator to help us complete this chart. Go to f of x. Type in the little equation, 3x minus 2. Once the equations get a little bigger and more involved, this is a really nice way to kind of evaluate a chart.
Yeah.
So you should know that this is going to make a line because it's mx plus b form. So hit graph. And here's my line. So when I just kind of visually look at the x value of 2, here's my x value of 2, and match it up in my calculator, we're trying to figure out the height, or where the y value is of the graph. So that's what we're trying to figure out. So graphically, what's going on when x is 2, what's happening with y. In the calculator, we've used that table of values a lot, but the table of values only gives us whole numbers for x and y. If you hit second trace, number 1 is a value, and if you hit enter, you can type in any x value that you want to that has decimals, and it'll give you a corresponding y value that also has decimals. So the first value is 1.9 in your table, so if you type in 1.9, it gives you 3.7. So my value is a little off that I had circled. So it's taking me right here where that x value is to. So see if you can fill in the chart below. So for each x value that's in the chart, just hit second trace, enter, and then type in 1.99. And then it just saves you from having to recalculate or re-enter that equation, especially once they get big. But that's the way to get a decimal value for x and a decimal value for y. Otherwise, x is whole numbers in your table of values. So fill in that little chart. Oops. So one way to try and look at evaluating a limit would be to look at numbers that are getting closer and closer and closer to whatever value we're asked to approach. So since the number we're approaching is 2, the 2 goes in the middle, and we pick a couple of values that are really close to 2 before it, really close to 2 after it. And then you get the number that is actually at 2, and it's 4. But looking at the numbers on the left and the right, you can see that as we're approaching 2, the y values of the graph plus you, or the function values, are getting closer and closer and closer to 4 as well. So a limit is what happens as you get closer and closer and closer to a number from both sides, the left and the right. So it says that f of x is getting closer and closer to 4, therefore the limit is 4. So since my y values are f of x, which are interchangeable, bless you, are getting closer and closer to 4, my limit would be 4. It says for this limit you can do straight substitution. Straight substitution means whatever your x value is approaching, you can directly plug that into your equation. And you'll do that for some of the homework problems tonight. So if I use straight substitution, I would take the limit as x approaches 2. My equation is 3. I'm approaching 2, so we would plug in a 2. The number that you're approaching gets replaced with x, or x is replaced with the number you're approaching. And then it was minus 2. And you can see by using straight substitution, directly entering that number into the equation, you get 4. It says we can use straight substitution because f of x is continuous, meaning it has no gaps or jumps in the graph. So if you make yourself a little graph on the side, we said this was a line. Jesse, where does this line cross the y-axis?
Negative 2.
At -2, and it has a slope of
3.
3. So it goes up 3 over 1. So right here is my value when x is 4. That's the number we're looking at. And graphically, we're looking at approaching 4 from kind of like both sides of my line, and they meet at the same number. And that's what the chart is showing you, that from both sides of that x value, they're meeting at the same y value. And that y value happens to be 4. So the limit of this function is 4 at x approaches 2. So we could find the limit as x approaches 5, when x approaches -3. This number down here can change. That kind of just tells us where to look at the graph. So if you look at the one underneath, we're going to try and do the same thing. The first couple homework problems, I think 7, 9, 15, 17, have you make your own chart. So here's another chart. We have a different function. So x cubed minus x squared plus x minus 1 all over x minus 1. So a little bit more involved. The first question underneath says, what is the value of f of x as x gets closer to 1? Will straight substitution work here? So let's try it. Straight substitution means whatever x is, plug it directly into your function. So if we take x and use straight substitution, that means I have 1 cubed minus 1 squared plus 1 minus 1, and then on the bottom 1 minus 1. So whatever the x value is that we're approaching is what goes directly in for x. That's straight substitution. You take your number, you plug it in. Sean, what do you get when you plug in 1?
Undefined.
Why is it undefined?
It's divided by 0.
It is divided by 0. What's the number on top? A 0. The number on top is also 0. What's 0 divided by 0 mean?
1.
Not 1. It's, yeah. What was that word you said? Indeterminate. It is actually a math word, indeterminate. When you have 0 divided by 0, literally you can't determine anything about the problem, as with straight substitution. So it's called the indeterminate. It has a term or a word for it, 0 divided by 0. Ask Alexa or Siri what happens when you divide 0 by 0. It gives you a little story about Cookie Monster. And him not having friends, that is right. And then at the end, it'll tell you the word that it's the indeterminate, so you can kind of ask Siri, Alexa tonight. So we cannot use straight substitution. In some problems, you can't just directly plug a number in. It's not going to work. So instead, we're going to complete this chart, finding out what happens as x approaches 1 for my y values. So again, when you're making the chart tonight, your number goes in the middle. You're picking 3 values that are really close to 1 that are less than it, 3 values that are really close to 1 that are greater than it. Whatever the number happens to be, it goes in the middle. Your pattern should look the same. Plug this in your calculator in for y equals. Make sure you're putting parentheses around the top, parentheses around the bottom. So go to your calculator, go to y equals. Parentheses around the top, divide, parentheses around the bottom, and then complete the chart. We're going to graph it in a little bit, but we're going to kind of answer, I couldn't fit it all on the same page, so we're going to answer the next part of it on the next page, and then we'll come back and look at the graph. But Gray, did you get some numbers in the chart?
Yeah,
What did you get?
I got 1.81, 1.98, 1.92, 1.998. Nothing.
Right, nothing here, we said that was undefined, so we'll put an undefined there, because 1 doesn't exist when you plug it in. And then on the other side of 1,
2.002. 2.02. And 2.2.
so what would you say the limit would be of this function as x approaches 1? What does it look like the numbers are getting closer and closer and closer to? 2. So looking at these numbers from the left and from the right, they're getting closer and closer to 2. So we would say that the limit is 2. This limit is not reached because it doesn't touch 2. It gets closer and closer to 2. So you'll have questions that says, decide if the limit is reached. If you can plug in the number with direct substitution, then the limit is reached. If you can't plug in the number with direct substitution, then the limit is not reached. It doesn't really touch that point, but it still gets closer and closer to the point. So it still has a limit. Questions? So if you can flip to the top of the page, again, unfortunately, I just couldn't squeeze it all in. At the top of the page, it says if you can alter the appearance of the function by using algebra and then substitution, we want to try and do that. So here's where the algebra part comes in. I'll write this equation again. So we have the limit as x approaches 1, and then it was x cubed minus x squared plus x minus 1 divided by x minus 1. How could we use algebra to alter the appearance, Jesse?
Factor the numerator, so it's x squared times x minus 1 plus, and then just 1 times x minus 1, and then you can factor out, like you can divide out the x minus 1.
So he is using factor by grouping. When there's 4 terms, group the first 2 together, group the last 2 together. He said factor out an x squared and factor out a 1. So we're changing the appearance using algebra, doing a little factoring here. So then our equation becomes x squared plus 1 times x minus 1, still divided by x minus 1. So the top part is factored. Once it's factored, Gray, what can you do?
All the x minus 1s are with each term, so you can cancel.
Yeah, they can cancel. So now our new equation says x squared plus 1. So we altered the appearance of the function by using some factoring and then canceling out the common term. Then you can take that number and directly substitute it in. So it says use algebra to change the appearance, then take that number and plug it in. So if we plug it in for x, we get 1 squared plus 1, which is 2. Which we showed on the previous page using a little chart and getting numbers that were really close to it, and now we can show using algebra. So yours doesn't have this filled in, but it says there is going to be a hole in the graph. Does anybody know why there would be a hole in the graph? What happened to the original equation? Jake? Gray, what did you do to the original equation after we factored? What did you do right here, Gray? You cancel out part of it. When you cancel out part of an equation, it creates a hole. So literally, we took a piece of the equation and we were like, woo, we're canceling it out. So you eliminated a part of the equation, and that creates a little hole in the graph. Not an asymptote, but a hole, wherever that equation was canceled or reduced. That's called removable discontinuity. So I took a little piece of it that was continuous and took it out of the problem. So we're going to go back and look at the graph. We're going to flip it to the previous page. And we're going to try and graph this. So the function we're graphing is x squared plus 1, because that's actually the function that we changed. Emily, what kind of graph is x squared plus 1 going to look like? A parabola, and that parabola starts at 1. So it starts up at 1. It's a parabola that goes up as well. It faces up. So I would go over 1, up 1 on both sides because 1 squared is 1. Over 2, up 4. But that's where my hole in the graph is. That's the part that was eliminated from the problem. Nope. My first one is where the hole was eliminated from the problem when x is 1. Over 2, up 4. Over 2, up 4. So the hole happens where the part was removed, the part that Gray removed from the problem, the piece that canceled. So now there's a little hole in the graph, but the rest of the graph exists. So we still have a parabola. The parabola goes on forever, beyond the hole, before the hole, but that little part that was removed creates the hole in the graph. So there's still a limit, but the limit isn't reached because there's a hole in the graph. My piece is missing. Questions? So anytime you factor and remove something, that's called removable discontinuity. It was continuous, it would initially be continuous, but it's undefined somewhere. And that piece that we remove, forcing it to be defined, creates a little hole in the graph, not an asymptote. We talked about that back in chapter 2, at the end of chapter 2, but that was so long ago. And we didn't call it removable discontinuity, we just said it was a hole in the graph. So if you look, there's a definition, flipping back, underneath, that talks about a limit. So a limit happens when your function or your y becomes arbitrarily close. What's arbitrarily close mean? Indeterminate? Infinitely gets closer and closer and closer and closer to that number. It might not touch it, but it's going to get really close to a unique number L as my x approaches a value of c. So whatever x is approaching, if my y value gets really, really close to it, we say that is our limit of L. And it says from either side. So that means we have to look at both the left and the right. So the limit would be the number L if my graph gets closer and closer and closer to a value. It doesn't have to touch it, it doesn't have to be that value, but it has to get really close to it. So a limit doesn't always have to be reached. Just like the speed limit. Some people reach the speed limit and go beyond. It's a suggestion, what a lot of people think, right? The speed limit is a suggested limit. So
Do
our
you always
limit,
drive below the speed limit, Miss Kane?
What?
Do you always drive below the
well,
speed limit?
I have 2 kids in the back of me who are continually like yelling at me, Mom, you're going 42 miles an hour and it says 40, because I have a stupid little sign like that says what the speed limit is on the road, and then next to it, it gives them a digital readout, so they know what the speed limit should be and what my little digital readout says. So yeah, I'm always like that. Yes, I try my best. Like I told them, like 5 is okay. It's okay.
Legally 11 is it?
Legally 11 is okay. Okay, there we go.
Morally 50
That's
is okay.
still get a ticket.
Yes, it's more morality.
Questions so far about the 2 problems we did? So the first one was direct substitution. It had a limit. The limit was reached. The second one we used factoring and canceling. It still had a limit, but the limit was not reached. So we're going to look at a couple of graphs. A lot of this is kind of looking at graphs, also thinking algebraically. It says the existence or non-existence of f of x when x equals c has no bearing on the limit. Right? So like, what the heck does that mean? That always helps to kind of look at a problem to understand what we're talking about. So here we have a piecewise function. It has the y value of 2 and the y value of 0. Y is 2 when x doesn't equal 3. Y is 0 when x does equal 3. So we have to try and think, what is this piecewise function talking about? When you're graphing a piecewise function, you're graphing one part at a time. So the one part is when y equals 2. The other part is when y equals 0. And then it gives you 2 conditions. So let's look at the bottom condition. It says y is 0 when x equals 3. What does that create in your graph? Y is 0 when x equals 3. Jesse? A point. So if you go to the x value of 3, that's on the x-axis, my y is equal to 0. So that creates a point at 3, 0. That's what that bottom part means. So my y is 0 when my x is equal to 3. What does the first part do, Greg?
It makes it an empty point.
It makes it an empty point, so when x doesn't equal 3, my y is 2, so it's empty, that's where we put a hole. And then what else do you draw there? You do. You draw the horizontal line, because if you have y equals 2, it's equal to 2 any place except where x is 3. So, nice job, Abby. It's a horizontal line. It can't equal 3, but it's going to be 2 at any other place. So this is a piecewise function. I have a point at 3, 0. I have a line at y equals 2, except at the value of 3. So underneath this, it wants you to evaluate f of 3. Well, this is really saying what's happening when the x is 3. So what's happening when x is 3, Abby? Y equals 0, because that's my point right here. X is 3, y is 0. F of 3 is equal to 0. That's really writing it as an ordered parent function notation. But the second question underneath says, what is the limit as x approaches 3? So to approach 3, you have to have movement in your line. And when you approach something, you're approaching it from the left and from the right. You can't approach a point because it's a point. You can't come to a point from the left and the right. But if I follow my line from the left and the right, Abby, the y value is approaching
3.
What's the y value right up here?
Oh, 2, sorry.
2. That's okay. My y value is approaching 2. So a point doesn't have a limit. It's just a point. But a line has a limit because a line I can move into a certain value. So right here is still where x is 3. Yes, f of 3 is 0 because that's the point. But the limit of the function is actually 2 because the part that has the piece that's going to move in towards a number would be 2. Questions on that? So we're going to look at another one of these. If you go underneath, yours is not written in, but if you can write this function in at the top for number 4. F of x is equal to 3 when x is less than 2, and 5 when x is greater than 2. So again, this is saying I have a line at y equals 3. We have a line at y equals 5. The line exists at 3 when it's less than 2, and at 5 when it's greater than 2. So my suggestion would be go to where x is 2. Right here's where x is 2. Then less than means, what do we place at 2? It's just less than. An open circle. So I'm going to go to the y value of 3, place an open circle, and then which way would we graph that line then?
We would draw it
Yeah, you draw it to the left. So there's my line on the y value of 3, showing x is less than 2. It's to the left. So then the second one is when y is 5, and again it says greater than 2, so that means
It would be an open circle and a line.
open circle and the line going to the right. So that's my piecewise function. I have 2 parts to it. I have one above the other because they have 2 different y values. So now that we have the graph, the question right here, this is the actual question. We want to find the limit as x approaches 2 of the function that we have drawn. So when you look at a limit, use your little fingers. They need to approach the same number from the left and the right. So if I look from the left, my left side is coming in right here. My right side is coming in up top. What would the limit be? Why not, Jesse?
Because they're like the left and right side are approaching different numbers.
So the limit does not exist. That's what DNE means. He said it's approaching 2 different numbers. So So a limit must approach the same number from the left and the right. Your fingers need to meet at the same vertical value. If one is approaching 3 and the other one is up at 5, they're not meeting at the same y value. So if they don't meet at the same y value from the left and the right, there is not a limit. Questions? So if you flip over, we're going to look at 3 examples, just trying to look at these limits not existing. Got another piecewise function. This is the final piecewise function, then the other 2 are regular functions. So we're going to try and graph this. You'll be asked to graph a piecewise function, number 31 tonight. It says, limits don't exist if the function approaches a different number from the right side than the left side. If that happens, you can write D, N, E. It might be asked to explain why. So we have an equation, negative x plus 3, when x is greater than or equal to 0. My second equation is just y is equal to negative 3 when x is less than 0. So I'm going to start with that second one. So y is negative 3 is that horizontal line we graphed 2 times already. So now going down to negative 3, less than 0, open circle to the left. And it's at 0 because it says less than 0. So y equals negative 3, we're down at negative 3. Open circle, less than means left. When we graph the next one, it's negative x plus 3. Emerson, where's that graph starting?
Sorry, you just did that one.
Yeah, I did the bottom one, sorry. The top one, where's the top one start?
So it's at 0, close circle, and then it's going to be at 0, 3,
Excellent, so down to the right. So we're going up to 3, close circle, because it says equals 0, and then he said down and to the right. So down 1, right 1. And you're connecting that to have a line. So there's my piecewise graph. Abby, does that limit exist? No. This should say as x approaches 0, not 2 down at the bottom. That's my typo there. So the limit as x approaches 0 does not exist because it's approaching 2 different numbers. It must approach 1. So if it has 2 different y values at the x that you're looking at, then the limit does not exist. So looking at the next one, it says if the function oscillates between 2 fixed values, then the limit does not exist. What's oscillates mean? A lot of good words today. Emerson?
like rotating and changing.
Yeah, rotating, changing. So kind of bouncing back and forth. I'd like you to put this equation in your calculator. So we have the sine of 1 over x. So 1 divided by x. And then hit graph. You see it kind of looks funky. You don't see anything? Maybe if you didn't do Zoom 6, you can do Zoom 6. Did anybody get anything? Yes? Okay. Nope. I'm in radians. Maybe put it in radians. That might help.
That's probably.
Put it in radians.
That's it.
So what I'd like you to do is hit zoom in and just hit enter. We're going to zoom in at the origin, 0, 0. So you can kind of see a little bit that something's going on at 0. The calculator is very tricky because it looks like it's stopping at 0, but it really is oscillating back and forth at 0, which means it's kind of bouncing back and forth between the same 2 values. So this does not exist. Going back to my calculator, this is kind of what it looks like. I'm going to draw a little bit of a sketch here and kind of make it like oscillate, and then it kind of humps back over. So oscillate means it's bouncing back and forth infinite times around that number. So if it's hitting two different values, then it does not exist. Sometimes the calculator is very misleading.
When you like zoom in, it looks like a barcode.
So how many times did you zoom in, Emerson?
Just 3 or 4.
3 or 4? Zoom in one more time here.
Yeah.
Oh, you can zoom in and before it's curved.
So there you go. This is at least, this gives you a better idea. Kind of shows you that bouncing back and forth. I zoomed in
A lot
twice.
more.
Wait, zoom in a little bit.
Yeah.
Just hit.
There we go.
So if you're kind of thinking what's going on with the calculator, zoom in a little bit more to see the information that's happening. There's one more underneath where a limit may not exist. So go back, zoom out of your calculator, hit zoom 6, that always gets you back to the regular screen. We're going to type in 1 divided by x squared. So go back to y equals 1 divided by x squared. And then hit zoom 6 when you graph, and it'll go back to the regular calculator screen. Zoom 6 takes you back anytime you tweak your calculator.
And you have to hit zoom 5 to go back to square.
You could do zoom 5 to go back to square if you'd rather have a square, yes. Zoom 6 is the
Thanks,
standard.
Emerson.
So if you make yourself a little sketch here, our calculator kind of looks like this. I have these two hyperbolas, because this is a rational function. It says the graph can approach infinity, even though the book says this limit does not exist. For calculus sake, we will say that this limit approaches infinity. So both sides of my graph are both going up to positive infinity. So this limit, we would say, approaches positive infinity. So if they're both going to the same number, then it has a limit. However, if one would go to positive infinity, the other one would split and go to negative infinity, then it would not have a limit. So both of them have to go up to the same value, and then we would say that has a limit of positive infinity. So the back of the book is going to say this one doesn't exist. We're going to say it does, that it's going to infinity. Questions? So there's 3 properties on the back page that I want you to look at. I don't think we'll get to the ones underneath that, but we'll at least look at these 3 properties. If you have a horizontal line, so this would be like having the limit as x approaches 3 of 7. Then the limit is whatever the value is of the horizontal line. So this makes a horizontal line. So if you have a horizontal line, the y value is always 7. So this would be equal to b. Here's my little example. Whatever the b value is. The number 2, if you have a function that is just an x form, God bless you, whatever number you're trying to approach is going to be the limit. Because when you plug that number in for x, if I plug a 5 in for x, I get a 5. If I plug a 7 in for x, I get a 7. And then the last one, if you have it raised to a power, my limit would be whatever the power is, not a square. So whatever c is to that power. So if I'm approaching 3, I plug in 3 and I get 3 squared. So your homework tonight, you're going to be making a couple of charts. Whatever the x value is you're approaching goes in the middle of the chart. You pick 3 numbers that are really close to it that are smaller, 3 numbers really close that are larger. Others are going to ask you to look at